Okay, just a quick walkthrough of the exploration on some very special Riemann sums. So we want to be able to calculate the area under the curve of the square root of x from 1 to 4. That's what the goal of the activity is. So we're trying to find this area here. And really, we don't know how to do that yet, other than with Riemann sums. So we can estimate it. So we're going to be estimating using trapezoids with 3 subintervals, which means each subinterval has a width of 1 because we have a total width of 3 on the total interval. So to find the area of a trapezoid, we're going to do 1/2 times the base, which is the same everywhere. And then the first trapezoid would have 2 heights, f of 1, f of 2. The next one would be f of 2, f of 3. And then the last one would be f of 3 and f of 4. So when you add all that together, I did all that over here on Desmos. And you can see the calculations right over here. I get 4.64626436994. Okay, that's good. Now, that is an underestimate because the curve of square root of x is concave down. All right, so we know that's too small. We're going to do something else. We're going to do a midpoint Riemann sum. And a midpoint Riemann sum, before we even do it, we know a midpoint Riemann sum is going to be too big for a concave down curve. So the midpoint of each one of those subintervals on 1 to 2 is 1.5. So I'm going to do f of 1.5 to calculate the height, and f of 2.5 and f of 3.5. Those are the 3 heights. Each of those subintervals still has a width of 1. And then the calculations are over here in Desmos. So 4.67 and change is too big. So I have a value that I know is too small. I have a value that I know is too big. And if you remember the story of Goldilocks, right? She went into the bear's house and she tried the bed, she tried the soup, the porridge, till she found one that was just right, right? This porridge is too hot. This porridge is too cold. This porridge is just right. Okay, we've got a Riemann sum that is too big. We've got a Riemann sum that is too small. Maybe we'll get one that is just right. So in number 3, that's where we're headed. Okay, so on each one of these, let me explain. It's a little weird at first glance, but on the first subinterval, so on the first subinterval k equals 1, they're asking us to use this point, 1.48, etc., as the value, not the midpoint, but they want us to use this randomly selected point on the interval 1 to 2. Same thing about the other 2 subintervals. This so close to the midpoint, but it's just random, just a random collection of digits. So to calculate the Riemann sum for that, using those sample points, right, we want to do the width of each subinterval, which just so happens to be 1 on each subinterval. But now the height is f of those 3 random points. So f of 1.48, f of 2.49, and f of 3.49. And over here in Desmos, I have calculated that to be 4 point lots of 6s. Now, could that be truly the area, the exact area under the curve? Because that's right in between those first 2 values that we got. So maybe these values aren't necessarily random. All right, let's keep going. All right. Now we're asked to do it again, but instead of 3 subintervals, go more subintervals, right? We just theoretically know that more subintervals is going to be better. So now, same story. We have 6 subintervals. They're all a half wide, and we get these random values. So you notice that 1.245 is on the first subinterval, 1 to 1.5, and then subsequently all the other ones. So similar story to number 3. We're just going to multiply each one of those by a half because the width of each subinterval is a half, and then f all of those x values, and the calculation is 4.668. I mean, virtually 4 2/3 exactly. No funny business way down the line. Okay, this is weird. How is this connection working? So we get this problem about a new function, g of x, 2/3 x to the 3 halves, which is not the function we're trying to find the area underneath. It's just this other function out of the blue. We want to find the point in the open interval 1 to 1.5 that that the mean value theorem guarantees happens. Now, the mean value theorem, that's that one that connects the average slope on an interval to the instantaneous slope. So it connects the derivative, g prime, at a c value, to the average slope on that interval, which would be the difference between the y values, g of 1.5 minus g of 1, divided by the width, which is 0.5. Okay, so I've done those calculations of that right side of the equation there on Desmos. You can see over here, I've defined g of x. I've calculated that value and just called it c just because it's easier. I didn't have to type in those numbers again. So I get that the derivative of g, which by the way, derivative using the power rule would be drop the 3/2, so that multiplies to 1, subtract 1 from the exponent. So the derivative of g is x to the 1/2, which is the function we're trying to find the area under, by the way. So g prime at c is c to the 1/2, and then the calculation is 1.116, blah, 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 blah. Solve for c by squaring both sides, and you get 1.245, etc. Now that number is supposed to ring bells. Does it? Is that my phone number in there hidden some? Oh no, wait! That value is the same value that they wanted me to pick in number 4. I think there is a connection. Methinks those were not random whatsoever. So the connection between the function g that we just played with in 5 and the function f that we found the area underneath is a derivative relationship. The derivative of g of x does so happen to be f of x. And I think after this exploration, the area under that curve is 14/3. Now, if you want to know more about why this connection is working, you're going to want to go check out the next video. Peace.